Yeah, great. Thanks a lot for the invitation again, and it's been really nice being here. Thank you guys for slogging through 3 lectures on this material. So I'm going to talk about algebraic K-theory today, and I understand that's a little technical. It is for me, but I'm going to try and keep things at a high level, and I'm happy to answer any questions to the best of my abilities about this material. So please feel free to ask questions about it. So this goes. So I told in the first couple of lectures, I've told you about the kind of thing prismatic cohomology is trying to do, the kind of problem it's trying to solve, namely relating sort of topology and algebra in certain contexts. But one of the motivations for the discovery of the theory was actually something slightly different. It came from topology, and so let me tell you about the origin story. And so the story begins with a very classical result in algebraic topology. So this is essentially a combination of the work of Atiyah, Hirzebruch, and Bhatt. So it's a combination of what's called the Atiyah-Hirzebruch spectral sequence and Bhatt periodicity. But it's a result that gives you a tool for computing a generalized cohomology theory for a topological space, if you know, provided you know how to compute the usual cohomology of the topological space. So let me just state it informally over here. So for a reasonable, which I will definitely not spell out, reasonable space, and I really mean like classical topological space, X. The invariant that I want to talk about is the complex K-theory of X. So this is a generalized cohomology theory. It takes as input the notion of complex vector bundles on X. And K0 would just be, you look at all possible vector bundles on X, isomorphism classes of it, and then you impose a relation that says that if one vector bundle is a direct sum of 2 other vector bundles, then the class of that vector bundle is isomorphic to the, or is identified with the sum of the classes of the pieces. And a slightly twisted version of that, where if you have a short exact sequence, then the class of the middle guy is the sum of the classes of the outer 2 pieces. So it's a very natural construction. It was first actually done by Grothendieck in algebra, so for algebraic varieties, and then to define an abelian group, which is called the Grothendieck group. And then I believe it's Atiyah and Hirzebruch that noticed that if you try to do this in topology, the group that you define is actually the zeroth cohomology group of a whole cohomology theory, which is complex K-theory. And so that's the theory I want to talk about. So for a reasonable topological space, there is this invariant called complex K-theory. I'm thinking of it as a topological space. So it has a bunch of homotopy groups, and these homotopy groups are called the K-theory groups of X. And the result is that there is a recipe for computing this in terms of the usual cohomology of X. So the precise statement is, for a reasonable topological space X, there exists a filtration on the space whose associated graded pieces are computable. So the ith associated graded piece of the filtration is essentially a copy of singular cohomology of X, and there's some shift. So I'm trying to state things at some informal level here. A formal statement would be that there is a spectral sequence where the E2 term goes from the usual cohomology of a topological space, and the E infinity term is the complex K-theory of a topological space. If you're more fancy, you can restate this in terms of filtrations on spectra, and then I think it's literally true as written. But very roughly, there's a recipe for computing K-theory in terms of singular cohomology. Okay, so that's kind of the situation. I think this was the situation in, I didn't look up the years, but probably I want to say 60s. And then in algebraic geometry, Quillen, inspired by the massive success of complex K-theory in topology, wanted to define an algebrogeometric analog of K-theory. So Grothendieck gave us K0, topologists define all the kns, and so now in algebra we also want all the kns. And so Quillen defined this thing called the Quillen K-theory of a commutative ring or a scheme or more general objects. And it's impossible to compute, as I said in the first lecture, but it's a fundamental invariant. It's deeply connected to various conjectures in arithmetic geometry. But one of those conjectures was something that was first noticed by Beilinson, which is the analog of this statement is missing. And so the goal of this talk is to describe an answer to one version of that question. So it's to describe a variant of this assertion or of this statement for algebraic K-theory, and it'll be slightly modified as follows. So X here is an algebraic variety, say, or more schemes, rings, whatever. Without the subscript étale, this is Quillen's algebraic K-theory space p-adically completed. And the étale means it's a certain modification of algebraic K-theory that makes it easier to compute. But of course, there's a price you pay. You're no longer computing algebraic K-theory, you're computing this modification of it. In the p-adic context that we are going to be working in, it's not a very serious modification. So for us, X will be a p-adic variety. And in this case, this étale subscript is, I mean, it does change things, but not so drastically. So I'm going to mostly suppress that, although maybe I'll come back to it at the end of the talk. And essentially, the format of the answer is going to be that there's a very similar statement, except instead of singular cohomology, you use prismatic cohomology. Or more precisely, something you define using prismatic cohomology called symptomic cohomology. And so this was actually one of the motivations behind the discovery of prismatic cohomology. We were looking for a filtration like this on K-theory, and then the graded pieces of that filtration would be called prismatic cohomology. And so I want to just describe how this answer looks. Okay, so that's the plan. Let me just make some informal comments. So, yes. Yeah, so I was about to, that was going to be the first comment. So if you ignore the subscript étale over here, and if you ignore the p-adic completion, so if you just ask about the version of this question for just algebraic K-theory on the nose, such a filtration was also, this was conjectured by Beilinson, that there is a filtration on algebraic K-theory where the associated graded pieces are given by something called motivic cohomology, which is essentially Chow groups. And so this filtration, I think, has been defined in the work of a lot of people. Bloch, Levine, Blavatsky. I didn't write down all the names, so let me not. But such a filtration exists. From the perspective I want to advocate in my talk is that the E2 terms, so the associated graded pieces, are given by motivic cohomology, which is really hard to compute because algebraic cycles are hard to work with. It's not so easy to find them, and it's not so easy to prove that two are the same. And so really we want a filtration where the graded pieces are much easier to compute with. And so the filtration is going to be compatible with the motivic filtration on algebraic K-theory via some comparison map, but the feature is going to be that the E2 term is easier to compute. Sorry, does that answer your question, Roy? Yeah. And the other question I wanted to make is, you notice that there's two appearances of P. X was a p-adic variety, and I was doing p-adic completions on K-theory, meaning I'm looking at the p-adic completion of the cohomology group. This is why the theory that I'm talking about is new. So if X was p-adic, but you were completing at a prime L that was not P, this story is much more classical. It's understood by the work of Thomason, and then Suslin and Gaber, and so on. It's really the interaction between the coefficients of where X, of the field where X is defined and the coefficients of the cohomology theory that gives us a Hodge theoretic flavor. Okay, so modulo all those technicalities, I'm going to try and tell you a version about this theorem in algebraic geometry. Are there any questions about where we're going? Yes, I'll come back to that. Yeah. Great. So let's put K-theory aside for the moment. I need to now tell you a little bit more about the formal structure of prismatic cohomology. I've so far just more or less used it as a black box that relates to other things. Let me tell you a little bit more about what the invariant precisely looks like. So this is the format of prismatic cohomology. And I will, for simplicity, I'm going to restrict to the case for axis and affine variety. So I'll just formulate everything in terms of commutative rings rather than geometric objects. You can put a spec in front of the commutative ring if you care, and then get more general statements. It's just notationally slightly easier to work with affines. So let me do that over here. So R is going to now be the basic geometric object. So it's the ring of functions on X, and we can work in sort of more or less complete generality. So R is going to be a p-adically complete commutative ring. For example, R could be a commutative ring where P is 0, or some power of P is 0, and that's extremely interesting. Okay, so that's the input data. You should think of this as the ring of functions on your space. And then the output of prismatic cohomology is a bunch of invariants that are related in some way. So let me tell you what some of those invariants are. So the most basic invariant is what's called the prismatic cohomology of R, prism R. And so what kind of an object is this? It's really a chain complex of abelian groups, and it has a multiplication on it. So one way to write it is that it's a commutative algebra object in the derived category of abelian groups. This is a very fancy way of saying I get a bunch of cohomology groups and I have cut products on them. So I can go from hi and hj to hi plus j. But it's sort of better to think of it as a more structured invariant in this form for some of the things I'm about to say. So, okay, that's the basic invariant. This invariant comes equipped with a certain invertible module. So what's called the Broykian twist. So this is an invertible module over this commutative ring, meaning there is a different invertible module where I put a -1, and the tensor product of the two of them is a trivial module. It comes with a Frobenius. I mentioned this in the first talk. Let me just write it. So I will call this the Frobenius, although it's a meaningless statement because it's just an endomorphism so far. In some very literal sense, it's a lift of the Frobenius mod P on this object. So it sort of feels like a Frobenius. And there's one more piece of structure I need, and then we can actually do things. So this is supposed to be some p-adic version of the de Rham complex. The de Rham complex has a multiplication on it, so it satisfies the first property. The shift over here just corresponds to shifting the filtration on the de Rham complex. The Frobenius really has no counterpart in the de Rham story, but there is a filtration. So there's something called the Nygaard filtration. On this invariant. And if you're thinking of this as a ring, this is a filtration by ideals. So they multiply nicely. Fill I tensor fill j goes into fill I plus j when you multiply, etc. And these objects are supposed to interact in some way. So the defining property of the Nygaard filtration is that it's not quite preserved by the Frobenius. The Frobenius doesn't take fill I to fill I, but it does after you twist it by I. So there's what's called the divided Frobenius map, which goes from fill I of the ith Broykian twist into the ith Broykian twist.
What name are you?
Oh, sorry, I didn't. Thank you. So this is the Breuer-Kissen twist. Yeah, sorry, I should have written that. This is the analog of the Tate twist in this world. Okay, so I apologize. It's a bunch of notation, but this is what the formal structure of the invariant looks like. There's a chain complex, there's a Frobenius, there's a filtration, and they interact in some way that involves this twist. At first pass, the twist can basically always be ignored. So if you don't want to keep track of all the data, then just ignore all the twists, and the theory still gives you something useful for rings of characteristic P, for example. So these are the invariants. As I was saying, for the K-theory application, it's not quite prismatic cohomology that's the answer to the question of what's the analog of the Atiyah-Hirzberg theorem, but rather something you derive from it. And so this thing that you derive from it is the following. It's called the symptomic cohomology. And that really is the sort of true invariant here. So Zp of I evaluated on R. So this is called the ith symptomic complex of R. And it's basically defined by observing that this Frobenius map, it goes from phi I of something to something, but I also have an obvious map from phi I of something to something, which is just the inclusion map. And so I can contemplate the difference between the two. And so it's the fiber, or the kernel in some derived sense, of the difference of the two maps. So Frobenius -1 going to prismatic cohomology twisted by R. Okay. So I think I haven't looked through my entire talk. I should look through my entire talk before I'm making the next statement, but I'm not going to. I think it's safe to more or less ignore everything on the board except this last invariant, because that's the thing we'll actually care about. But I wanted to explain to you roughly where it comes from, like what the relationship of this invariant is with prismatic cohomology. It's not literally the same, but they're pretty close to each other. Okay, so let me give you some easy examples of what this looks like. So first is the zeroth Tate twist. So zeroth symptomic. So this twist over here, I'll also sometimes call the Tate twist or the Breuer-Kissen twist. So the zeroth one is very easy. So if you're doing a zero twist, the filtration is not doing anything. The twist is not doing anything. So you're looking at the difference between the Frobenius and the identity. And this is some classical thing in algebraic geometry called the Arden-Schreier sequence, which will tell you that this is the étale cohomology of R with coefficients in constant sheaf Zp. So it's essentially a version of the constant sheaf in this setting, the zero Tate twist. Okay, so this is the constant sheaf. So in weight 0, you don't learn anything new. But in all higher weights, the invariance is new. And for weight 1, I will tell you a theorem that this invariance lets you prove that was inaccessible before that. But maybe before I do that, I want to just give you an example of a specific commutative ring R where you can compute everything. So take R to be K, which is a perfect field of characteristic P. For example, just the finite field Fp. Okay, so in this case, we can be explicit about everything. So this prismatic complex prism R is what's called the ring of bit vectors of K. If K is Fp, this is just the p-adic integers Zp. The Frobenius is the usual Frobenius on the bit vectors. I don't know how to write this. Phi is actually what you normally call the Frobenius. And the twist is trivial, because there are no invertible modules over the string. And then the only piece of information I have to give you in order to describe what the symptomic cohomology is I have to tell you what this map looks like in this example. And it turns out to be the following. So, oh, I guess I have to tell you the Nygaard filtration, sorry. So the Nygaard filtration, in this case, it's a filtration on the width vectors of K. This is a DVR. DVR doesn't have that many interesting filtrations. You just take powers of the maximal ideal. So it's the p-adic filtration. And the divided Frobenius so the divided Frobenius is supposed to be a map from fill I back to the ring. So in this case, it goes from P to the I times W of K to W of K. And it's the map that identifies the two. So phi I from P to the I times W of K to W of K is actually an isomorphism which sends P to the I times alpha to phi of alpha. Okay. So what's the reason I did all of this? It's to give you an exercise. If you're bored and like this stuff. So the exercise is to compute the symptomic cohomology using the information given to you. I've defined everything for you explicitly for this particular R. And the exercise is to show that Zp of I evaluated on R is equal to 0 for all I not equal to 0. So in other words, you're looking at so for I equals 1, say, I'm looking at the map from P times W of K to W of K, which is the difference of the inclusion map, and this map, which is sort of Frobenius divided by P to the 1. And you have to check that that map is an isomorphism. Okay, so again, the precise nature of things doesn't matter. I just want to convince you that this is a pretty computable invariant. And I actually told you the computation in this case. So this is what this prismatic cohomology and symptomic cohomology invariants look like when the input is a commutative ring. And now we can go back and start talking about K-theory again, unless there are questions. So what are the main theorems here? I'm just going to write down two theorems. So I'll call it theorem A. And this is really the combination of the work of a ton of people in algebraic K-theory. The sort of punchline at the end was provided by Clausen, Matthew Morrow, and also in my joint work with Morrow and Schulze. So these are all from roughly 6 or 7 years ago now. And it's exactly realizing this goal that I set forth earlier. So there exists a filtration on this thing that I call the Étale K-theory with p-adic coefficients whose associated graded pieces are computable. So more precisely, the ith associated graded piece is exactly given by this symptomic cohomology. So with Gur I is Zp of I evaluated on R. And then you have to shift it properly. So in the Atiyah-Hirzberg spectral sequence, what was happening is that all the graded pieces were the same. They were just copies of singular cohomology with shifts. In this world, all the graded pieces are not the same. The ith graded piece depends on this ith twist of R. And so this is maybe a slight answer to Roy's question earlier, that you don't quite have Bott periodicity in this setting. There is some kind of weak version of it, which I'll mention in a few minutes. But in particular, this is telling you that there's a way to compute this invariant, or at least its homotopy groups, provided you know how to compute these invariants. And these invariants, I tried to tell you earlier, were quite computable because They're related to prismatic cohomology. And so I wanted to just mention some examples of how this gets used now. Sorry, I realize this is not a very K-theory heavy audience, and so I'm sorry for the notation, but please ask questions. And I will try to mention some non-K-theoretic applications as well. So that's the theorem, and then maybe I make a remark, or I can formulate a different theorem. So this theorem is really capturing a lot of information, and I want to just isolate the I equals 1 case of this theorem. So the first symptomic complex, which is what GER1 corresponds to, is something we have a definition for. On the other hand, it's supposed to be a filtration on something called related to K-theory, so something built from bundles, vector bundles, and so on. And so it actually also has a description in terms of bundles. And if you combine the two, you get something interesting. So understanding GER1 explicitly via the map from the Picard group. So if I give you a line bundle on R, I can definitely build a K-theory class. And if you ask me for the formula, I will probably get it wrong, but I think it's the line bundle goes to the class of the line bundle minus the class of R. So you have to subtract off the class of the trivial bundle from it. And so what happens is that you have this map from the Picard group of R, which is just the group of isomorphism classes of line bundles into K-theory. And it turns out that this exactly hits the GER1. And so if you think through what that will tell you, is you learn the following. So I'll call this corollary B, which has nothing to do with K-theory. So there exists an exact sequence where on the left-hand side you have, so I'll write it formally, so the étale cohomology of R with coefficients in GM. So the multiplicative group. This is some cohomology theory whose zeroth cohomology group is the units of R. The first cohomology group is the Picard group of R. The second cohomology group is the Brouwer group of R. And then things become out of control. P-adically completed. And this is exactly GER1. And so therefore it's given by the symptomic complex, which has a nice formula for it. So it's fill 1 of prismatic cohomology, mapping YFI minus 1 to prismatic cohomology. Okay, and so I just want to roughly discuss the structure of this. So on the left-hand side, you have some invariant which is related to the intrinsic geometry of R, things like line bundles on R. In the middle and on the right, you have things related to prismatic cohomology, which are much more computable because they're related to things like differential forms. And so this sequence over here, let me call this sequence star, it gives you a new tool for computing the Picard group or the Brouwer group in terms of differential forms. And in that sense, it's kind of a p-adic version of something classical, which is called the Lefschetz 1-1 theorem. So it's not as strong as the Lefschetz 1-1 theorem. The Lefschetz 1-1 theorem actually proves the Hodge conjecture for divisors. This doesn't quite do that, but it at least gives you a handle on what line bundles look like in terms of more computable objects. And I'll come back to an actual application of this in a few minutes. But I wanted to make one more remark before I get there, unless there are any questions so far. Yeah. Sorry, I should have. Maybe I will. I was going to mention this later, but absolutely. So in the situation where motivic cohomology is defined, so if you have something like smooth scheme over a Dedekind domain, for example, or a field, the symptomic cohomology can be identified with étale motivic cohomology. So that's the connection. But I believe from the motivic perspective, you sort of don't get any differential description of the motivic cohomology groups. It's only after this étale sheafification that you get such a description. Thank you. Yeah. Right. And so the other remark I wanted to make was, in the theorem I raised, there were a lot of attributions. And let me comment on the last two. So I mentioned Klaus and Matthew Morrow. And so roughly, what they do is they translate from étale K theory into some other invariant called topological cyclic homology, which is much easier to work with. So what they prove is that K étale of R with p-adic coefficients is the same thing as Tc of R with p-adic coefficients. And at the level of symbols, it doesn't mean much. But this theory called topological cyclic homology was invented by topologists for geometric applications. Like, I think one of the first things they proved using it was a version of the Novikov conjecture. And it has the feature that it's computable in terms of other invariants. So this is computed using other 3-letter or 2-letter symbols called THH, TC minus, TP, etc. So I'm not going to go into a definition of any of these invariants. All I'm telling you is that there's a way to compute étale K theory in terms of other invariants that are potentially easier. And I'm trying to mention this because there was something very parallel in symptomic cohomology. Symptomic cohomology was defined to be computable in terms of prismatic cohomology and the Nygaard filtration on it. And the two descriptions are compatible. So this DMS theorem, which was sort of the other attribution I mentioned earlier, what it really does is that it doesn't prove anything about étale K theory. It proves something about these invariants. So what it does is it's a variant of theorem A for these other invariants. So THH, TC minus, TP, and TC. And the only reason I did all of this work with all of this notation was to write the following line. So but the graded pieces are given by the following. So for THH, you get the ith graded piece of the Nygaard filtration. For TC minus, you get the ith level of the Nygaard filtration. For TP, you get just prismatic homology itself. And then for TC, you get the actual invariant you care about, which is symptomic homology. So this procedure, this elaborate procedure of starting with prismatic homology and all of these structures and building symptomic homology out of it has a complete parallel in the topological world, which goes back to the 70s, I think, of trying to build K theory or really topological cyclic homology from these other invariants. And so the new thing that we gain compared to what was known, let's say, 10 years ago is these calculations over here, and not just the ZPFI ones. Okay, sorry, maybe that didn't make any sense, but are there any questions? Yeah?
So are this notation just, I guess the CMM result is the prismatic.
Right.
And are these notations just for taking a prismatic?
Yeah, exactly. So the theorem is compatible with the filtrations in the nicest possible way. So étale K theory has a filtration by symptomic cohomology. TP has a filtration by prismatic cohomology. Étale K theory has a map to TP, which is a filtered map, and on graded pieces, it goes from the obvious map from here to here, and things like that, yeah. So theorem A is really just a filtered refinement of this package for computing algebraic K theory that topologists have been using for a long time now. Yes? Okay, so I want to mention now some concrete applications of this stuff. Two of them are things I already somehow mentioned in the first talk, and one of them is new to this talk. So applications. So one is this odd vanishing theorem that I mentioned before, but let me write it out properly now. So it's an answer to the question that Roy was asking about Bott periodicity. So for this étale K-theory object, we don't have Bott periodicity. Like the theory is not two periodic. Complex K-theory by Bott periodicity is two periodic, meaning if you input a point, or more generally just a contractible space, then K0, K2, K4, all of them are the same, K1, K3, and so on. Sorry. If you input a space, K0, K2, K4, etc. are all the same, and all the odd ones vanish. So Bott periodicity has two parts, the periodicity and the fact that the odd ones vanish. And so this is the analog of the latter in this p-adic setting. And so the statement is that if you look at the odd homotopy groups of K-theory, the p-adic coefficients, then they vanish locally in a certain sense. And the precise words I should say over here are symptomic locally on symptomic rings. But this is only for experts. This is this maneuver of, the statement that something vanishes locally is like saying that it's only on the K-theory of a contractible space that you get the odd dimensional groups vanishing, not on a general space. And so this is one corollary that you get out of this, and the key point of the proofs. So this is just a statement about algebraic K-theory. It doesn't a priori have anything to do with the filtrations that I've been talking about. But the way you prove this is you use the theorem, this theorem A, which was giving a filtration of K-theory in terms of symptomic cohomology. And you translate this into a statement about symptomic cohomology, which you can then prove by hand, or sort of. So via theorem A, this reduces to checking that the symptomic cohomology has the same property. So it lives in degree 0 locally. So you have to work through the spectral sequence, but if each of these guys lives in degree 0, then you immediately learn that the odd ones vanish, because that's how the numbers are set up. And so you still need to prove this, but now you translated the statement in topology or in homotopy theory to some statement in algebra, which might be more accessible. And it is, but it actually needs a serious input. So in my lecture yesterday, I mentioned the direct summand conjecture. And in the proof of the direct summand conjecture, Yves André proved a really fundamental lemma about some commutative algebra properties of perfectoid rings. And that's the sort of essential input you need in order to construct the covers that are implicit in this part. So use commutative algebra. More precisely, what's called André's lemma. To prove the vanishing. Okay, so I just wanted to mention this because I think it's a nice example of how in this subject, various fields of math where p-adic numbers are occurring end up talking to each other. Like, I don't think the mathematicians that were thinking about André's lemma were at all interested in K-theory, and I'm sure the converse was also true. And so, at least for me, that's very satisfying. Okay. So that was one application. In the first talk, I also mentioned this thing called the even vanishing theorem by Antio, Krause, and Nicola. So maybe I won't write it out again. But I will mention an application to algebra, which has nothing to do with K-theory. So it's to purity problems. And again, I think this was quite nice. So there's something called Gaber's conjecture. And it was proven recently by Chesnavicius and Scholze And it's a very, it's a rather simple statement about in algebraic geometry. So let's say X is a Noetherian scheme, and it's LCI. So LCI stands for local complete intersections. It basically means that it's defined inside something smooth by the right number of equations. So it's not too pathological. And Z inside X is a closed subset. Then the conjecture is about trying to understand when are certain invariants the same for X and for X minus Z. So the picture is something like here's X, and you should imagine Z is pretty small compared to X. So if X is a surface, then there's not much room for what Z is, because I can only draw so much. But I'm imagining X is like 100 dimensional and Z is like 5 dimensional. And in this situation, what you expect is that if you take some cohomological invariant for X and restrict it to the complement of Z, there should basically be no change in information. Like if you're thinking in terms of fundamental groups, if you have a loop outside of Z that can be contracted inside all of X, then surely you can choose a homotopy that avoids Z. Z is so small, you can just wiggle things around enough and avoid Z completely. And so that intuition suggests that there should be some kind of relationship between invariants for X and X minus Z. And this is what they prove. So let me write it over here. So the invariants they prove something for are the Picard group and the Brouwer group. And what they prove, actually I can write it here, that the Picard group of X mapping to the Picard group of X minus Z, here I have to say torsion. The torsion part of the Picard groups are the same if the correct condition holds. So if the dimension of, if the codimension of Z in X is at least 3. And the Brouwer, similar statement for the Brouwer group, which is something about central simple algebras for X and X minus Z being the same if the codimension is 1, if the bound is 1 better. Okay, so these results were conjectured by Gaber, and if you're an algebraic geometer, this should maybe be not so surprising. Like if you're thinking about the case of complex varieties, these are pretty straightforward, pretty easy to prove using some basic machinery of things like étale cohomology. The interest in, or the strength of this theorem is that it's applying in the case where classical tools didn't apply. So it's not about just varieties over a field. It's not about complex varieties. It's really about in complete generality. And in this complete generality, previously we had no tools for understanding these invariants. And now we do. We have this exact sequence star that I had on the board on this side. And that's kind of the essential ingredient in the proof of these theorems. So use the sequence star. Yeah. Sorry? Okay, so very good. Thank you for the question. So let me just write out what the sequence was, and then we can try to. So the sequence was saying something like, I might have a shift missing, but anyways. There's some sequence like this, and there's also a version of this. So you want to write down, you want to compare this sequence for X, which is now R, and also for X minus Z. And so you want to prove that the map from this complex to this complex is an isomorphism in low degrees, because Pick and Brouwer are the homotopy groups in low degrees. So you want to prove the analogous statements for these guys. But these guys are very close to the coherent cohomology of R. But the precise statement is that they are related to not just R, but differential forms on R. And differential forms on R, by that what I really mean is that the cotangent complex and its exterior powers. And so the cotangent complex is well behaved in the LCI case. You have your handle on it, otherwise you don't. Yeah. That's where the LCI assumption is kind of all over the papers in the subject, and this is more or less the source of it. Great. Okay, other questions? So again, as I said, I was talking about the applications of these theorems on filtering K-theory, and I mentioned the odd vanishing theorem. I mentioned the even vanishing theorem in the first talk. I'm not writing it on the board today, but again, I think that's a fundamental theorem. And then there is this kind of purely algebraic application that comes out of this exact sequence for computing different Picard and Brouwer groups using differential forms. So in my remaining time, what I want to do is I just want to talk about some recent developments. The subject is moving very quickly, and I think our understanding of it is also evolving rather quickly. But I should at least mention how we understand things now, with the caveat that this could very well change in a year. So I was talking about these filtrations on K-theory, and I said that there were several restrictions in what I was talking about. First of all, I talked about étale K-theory instead of actual K-theory. Secondly, I was talking mostly about the K-theory of commutative rings or varieties. But if you look at Quillen's original paper and the literature on algebraic K-theory, the input does not have to be a geometric object like a ring or an algebraic variety. It can be much more general. In particular, you're allowed to plug in rings that are of interest to algebraic topologists that are not actual rings, but some kind of homotopy rings. And so the story has been extended to that case recently. So these filtrations are called motivic filtrations. And so the motivic filtrations on the étale K-theory of R and all the cousins that I had earlier, like THH, etc., are now defined for a much more general R. And so I wanted to mention two things in this direction. So here I'm talking about the étale K-theory of a commutative ring. But what algebraic topologists want to do is not take a commutative ring over here, but rather a commutative ring spectrum, something like the sphere spectrum or complex K-theory itself thought of as a ring, and then you do K-theory of K-theory. So it's some kind of iterated K-theory, for example. And so this was done, the precise language I want to use is E-infinity rings, R. So classical rings are E-infinity rings, but E-infinity rings are much more general. And so this was in the work of Hahn, Roxeth, and Wilson last year. And I think for a while people thought that this was, well, okay, I think before the Hahn, Roxeth, Wilson paper, at least I thought that the existence of the motivic filtration on the étale K-theory or something is a strong sort of reflection of the fact that this thing has algebraic origin. It came from commutative algebra and wasn't some fancy derived thing. These guys are telling us you're allowed to take fancy derived things which are E-infinity. E-infinity stands for commutative. So the E-infinity part means it's extremely commutative. That's commutative in some best possible sense. And then very recently, so just I think a few weeks ago, this was extended to associative rings by Stragowski. And I think the motivation for a lot of these papers is the existence of this filtration was telling us about prismatic cohomology. It was essentially saying that the associated gradient of the filtration here is the theory of prismatic cohomology. And now that you have these generalizations, you get notions of prismatic cohomology for E-infinity rings, or more generally even E1 rings. So there's, for example, something called the prismatic cohomology of the sphere spectrum. I have no idea what it is. I think it's being investigated by these guys. Yeah. Yeah, this is really last, I think, just a couple of weeks ago. Okay, so that's one direction in which things are going. Another direction is to get rid of the étale over here. As I was saying, the theory is hard without the étale, which is usual algebraic K-theory is more difficult than étale K-theory. And related to that, the analogous filtrations on usual algebraic K-theory were classically only defined under strong conditions, like you need it to be a smooth variety over a field or something pretty close to it. There's work by I believe people have now figured out how to do it for essentially arbitrary varieties. So there's a motivic filtration on the K-theory of R with p-adic coefficients, not et al., just actual algebraic K-theory, for any FP algebra R, or for any ring R containing a field. So even complex varieties. And this is work in progress, so I don't think there's a paper yet, but there are several talks you can find. It's by Bachman, El Monto, and Morrow. So in other words, I'm saying that the existence of the motivic filtration is now something you can ask about for general rings, including non-reduced rings, which previously your hands were more or less tied. And they use theorem A and variants of it as input in what they're building. Okay, so these are results that people have. I think maybe even more exciting from my point of view is a conjecture. So Jacob Lurie has a very precise conjecture. And I will not formulate the precise conjecture here. I will just say it in a slogan. So the slogan is basically that there exists a prismatic stable homotopy theory. And so let me explain by a table what that means. And so this is sort of topology. And here's algebraic geometry. In topology, you have the theory of singular cohomology. And I've been trying to make the point that prismatic cohomology, or really symptomic cohomology from the point of view of today's lecture, is the analog. So here you have symptomic cohomology plus prismatic cohomology and the relation between them. Now, the entirety of today's lecture was about finding the analog for K-theory over here. So in topology, we have complex K-theory, which is a generalized cohomology theory you can evaluate on a topological space. And the counterpart to that in algebra is equivalent K-theory, so algebraic K-theory, plus the full THH TC package for computing it. So this machinery that topologists have built up to compute K-theory, which at the associated graded level is the machinery for computing symptomic cohomology from prismatic cohomology. But in topology, you can go a lot further. These are just the two of the simplest cohomology theories you can write down, but there are many more out there. So the next simplest one, in some sense, is elliptic cohomology. And we have no idea what goes here. So there should be some version of prismatic elliptic cohomology now, which one can say a lot about conjecturally, but one does not know how to define. And all the way down, in fact. So really, this is just a series of question marks. But Jacob has a conjecture for how to fill this in. It's an abstract theorem. It doesn't sort of construct the cohomology theory for you. It just proves that there has to be one with a specific shape with some properties. And so I think this is kind of a really interesting direction from the point of view of an algebraic geometer, because it's telling us that there are new invariants of algebraic varieties, a lot of them that we haven't found yet. And maybe those could be more useful in understanding torsion in phenomena than the sort of existing cohomology theories that we have. Okay. So I was going to say something about, well, let me try to say this. I have 5 minutes, right? So the last direction I want to mention, it doesn't have anything to do with K-theory, but rather it's a direction in which symptomic cohomology is evolving. So it's about geometrization of symptomic cohomology. And so what do I mean by this? So here's kind of the basic format of how things work. So the phrase geometrization over here refers to, I think this is something that algebraic geometers do, and I don't know how standard it is, but there are some objects you're trying to understand. And if those objects are given to you in the abstract, they're a little harder to understand. But if those objects live on an algebraic variety, sort of spread out over an algebraic variety, they're easier to understand. They localize on the space, and then you can do things. And so what this is going to be about is essentially realizing prismatic cohomology as coherent cohomology of something else. And so more precisely, let's say X is so the input data is a p-adic formal scheme. You can ignore the word formal if you're allergic to it. And then what we know now is that there exists an algebraic stack. Called the symptomification of X. X syn and a line bundle O of 1 on the stack with several nice features. So I'll just say two of them. So one of them is that the cohomology of the ith tensor power of this line bundle on the stack is just symptomic cohomology. So this is Zp of I of X. And so now you realize symptomic cohomology is really just cohomology of a line bundle on an algebraic stack that's much more friendly, at least to me. And then the same thing is true for prismatic cohomology. So there is a dense open substack called the prismatization inside the symptomification, such that if you compute the cohomology on this open substack, you get prismatic cohomology. So from the stacky perspective, the fact that symptomic cohomology was defined using prismatic cohomology, you have the map from symptomic cohomology to prismatic cohomology, becomes a restriction map. You're taking cohomology classes on this compactification and restricting it to the thing you're compactifying. And so what this buys you is there's now a much more general notion of symptomic cohomology. It's not just for these line bundles, you can do it for any vector bundle, and you get some theory of symptomic cohomology now. And so the basic principle that emerges from this study is the following, and then I'll stop. So the principle is that if you work with perfect complexes on the stack, so perfect complexes are sort of the natural generalizations of vector bundles if you want to allow slightly derived objects. These seem to be, well, everything is in quotes here. They seem to be playing the role of p-adic motives over X. And really, I mean sort of least p-adic motives. Okay, sorry, there are lots of square quotes here because I'm not making a precise statement. I'm just trying to indicate that we have now a definition of a category that feels like the category of p-adic least motives over X. And it has a lot of evidence going for it. I was going to mention some evidence, but maybe I will not do that because it's already 5:14. And I'm happy to answer questions about that later, but let me stop over here for now. It's in square quotes because, okay, there are various ways things, maybe there should be multiple layers of square quotes. So one of the square quotes is because it's a formal completion of something that was algebraic. or something that feels like it should be algebraic. That's pretty tame. The other scare quote is because the stabilizers that show up can be infinite type. So it's always a quotient of something finite type, but the thing you're quotienting out by can be an infinite type group scheme. But there's an example which is very simple where none of these features show up. So if you do it for spec FP symptomic, and let me just describe the mod P fiber of the stack. So I'll just draw a picture. You take the nodal cubic, and so this is P1 with 0 and 1 identified, if you like, and then you mod out by GM. It's that object. That one's pretty nice. So this for the square codes, if I tried to do this for A1 instead of oh, sorry, I was going to give some evidence for why this. Okay. Right, so what properties would one want from a category of motives over a space? I mean, I think this is a somewhat philosophical question, but Bailenson wrote down some list of axioms that any category of mixed motives should satisfy. And one of the axioms was that algebraic K-theory should have a filtration where the graded pieces are given by sort of internal harms in this category. And theorem A that I was telling you, combined with this isomorphism over here, is exactly saying that. So it's a version of Bailenson's conjecture in this in the setting of italic K-theory. Another property that a category of motives could have is that it should have realization functors to any sort of more classical p-adic cohomology theory. So I'm saying that this is kind of the universal p-adic cohomology theory for varieties over X. But there are more classical p-adic cohomology theories for varieties over X, like italic, crystalline, blah, blah, blah. And they should all be realizations of this. And that's also true. So there are functors from this to those classical categories of coefficients that take push forwards over here to push forwards over here, and that's some kind of a universality phenomenon. And there's one more piece of arithmetic evidence, but maybe I will not say that now.
Another question? Yeah, I saw you in the race conjecture. I saw you listed the logical series by height, like there's a complex case
right.
of height 1. The cohomology is of height 2, and etc. Is it expected that corresponding to each height there is going to be a theory of algebraic?
Right, that's exactly the conjecture.
And is it expected that there is some kind of chromatic phenomena that's
like what kind of chromatic? Sorry, what do you mean by that?
I know it's good. Maybe I'll ask you later.
So the more precise form of the conjecture is that if you, so in topology there's this calculation of Colin, right? That, sorry, I don't know who it is due to, but if you compute the endomorphisms of, maybe it's a definition. If you compute the endomorphisms of singular cohomology as like as a spectrum, then you get the C-node algebra. And so the conjecture, Lurie's conjecture, one version of it says that if you compute the endomorphisms of symptomic cohomology as a spectrum valued functor, then you get something which essentially looks like the classical C-node algebra. So for example, it has the same size.
You are expecting to know how to operations.
Right, and I think the way the conjecture works is that if you prove the statement I made about classifying all the operations, you can then reverse engineer that to build the things that give those operations.
Thank you.